So I'm just going to go through a pre-lab talk for the experiment measuring optical activity using a polarimeter. So first of all, I just want to mention and talk a little bit about carbohydrates, because we will be working with a carbohydrate molecule today. So carbohydrates are molecules that consist of carbon, hydrogen, and oxygen atoms predominantly, and are typically polyhydroxyaldehydes or ketones. And you have an example of D-glucose on the right, which you've met before, a polyhydroxyaldehyde. So examples of carbohydrates, it can be found in starch, fiber, the sweet-tasting compounds called sugars, such as glucose, and structural materials such as cellulose. So carbohydrates are chiral, and we've met chiral molecules before. A chiral molecule is a type of molecule that has a non-superimposable mirror image. And we have an example here on the right where we have a pair of enantiomers. There are non-superimposable mirror images, and we have an asymmetric carbon with 4 different groups attached. So carbohydrates, as I said, are chiral and can have two enantiomeric forms, the D and the L form, which are non-superimposable mirror images of each other. So here we have an example of that. We have D-erythros and L-erythros. They are a pair of carbohydrates. They are a pair of enantiomers. Chiral compounds rotate plane polarized light, and that means they are optically active. Achiral compounds have no effect on plane polarized light. They are optically inactive. So let's look at this a little bit more closely. So with our polarimeter, we use a polarimeter to measure the optical activity of chiral compounds. So within a polarimeter, you will have a light source, and the light source produces light, and that light wave will oscillate in all directions. That's our normal light. That light will pass through a polarizer. And what happens there is that we get plane polarized light coming out, where the light waves oscillate in a single plane only. So that is what we call plane polarized light, when we pass normal light through a polarizer to give us light that oscillates in a single plane. So with our polarimeter, we will generate plane polarized light from our light source and our polarizer, and that plane polarized light will pass through our sample tube. And in this example here, the sample tube contains an achiral compound, so it's not chiral. So in that case, the plane of the polarization does not get rotated, and the plane polarized light continues in the same plane. So let's look at a case where we have a chiral compound in our sample tube. So again, we have our light source, our normal light passing through the polarizer, producing plane polarized light. And then that plane polarized light passes through our sample tube containing the chiral compound. And because the compound is chiral, it rotates the plane polarized light. And we can measure this angle of rotation. And we call this the optical rotation alpha. And that is measured in degrees. So how many degrees the plane polarized light has been rotated. So a pure sample of one enantiomer rotates plane polarized light in one direction. That rotated either clockwise in the plus direction, or that's also called dextrorotatory, or anti-clockwise negative, called levorotatory. A pure sample of the other enantiomer of that compound will interact with plane polarized light differently and will rotate the light by the same magnitude but in the opposite direction. A racemic mixture, which is a 1:1 mixture of the two enantiomers, and if a compound is present as a 1:1 mixture of the two enantiomers, i.e. a racemic mixture, then the clockwise and the anti-clockwise rotation cancel each other, and there's no net rotation of the plane polarized light. In other words, the 1:1 mixture is optically inactive. So a racemic mixture is optically inactive, and you do not see any rotation. So a polarimeter measures the observed rotation alpha. And the value of alpha varies with the concentration of the sample, the length of the sample tube, the temperature, and the wavelength of light that you've used. So optically active substances have a characteristic specific rotation. And that's the rotation that is given, I'll explain that now. So the specific rotation is the number of degrees of rotation caused by a 1 gram per milliliter solution of sample in a polarimeter tube of length 1 decimeter, or 10 centimeters. So it's quite specific in what you have to set up. A concentration of 1 gram per milliliter in a polarimeter tube of 1 decimeter, or 10 centimeters in length. The relationship between observed rotation alpha and the specific rotation alpha t lambda is given by this here. So alpha t lambda, which is your specific rotation, where t is the temperature and lambda is the wavelength of light you've used, so you have to make note of those when you do a measurement, equals alpha, the observed rotation, divided by L, which is the length of the sample tube, multiplied by C, the concentration. So you make up your concentration, you multiply it by the length of the sample tube, your observed rotation is divided by that, and that will give you your specific rotation. Here's an example of R2-methyl butanol, which has a specific rotation of plus 5.75, and it's an enantiomer S2-methyl 1-butanol, which has a specific rotation of minus 5.75 degrees. This D indicates the sodium vapor lamp was used, and that will tell you that it has a wavelength of 589 nanometers. Now, enantiomeric excess, when you have more than one enantiomer than the other. The observed specific rotation can tell us whether a sample consists of a single enantiomer or a mixture of enantiomers. When only one enantiomer is present, we have an enantiomerically pure sample. An enantiomerically pure sample of S plus 2-bromobutane will have an observed specific rotation of plus 23.1 degrees. The specific rotation of S plus 2-bromobutane is plus 23.1 degrees. If the sample of 2-bromobutane has a specific rotation of 0 degrees, then the sample must be racemic. It must have equal amounts of S and R to give you a rotation of 0. If the sample of 2-bromobutane has a specific rotation that is still positive, but less than 23.1, then the sample is a mixture of enantiomers with more of the S enantiomer present than the R enantiomer, because it is rotating in the plus direction. If it rotated in the minus direction, but less than minus 23.1, then you would know you have more R than S present. The observed specific rotation can be used to calculate the enantiomeric excess of the sample. So to do this, to calculate the enantiomeric excess, you get the observed specific rotation divided by the specific rotation of the pure enantiomer. So the observed rotation divided by the specific rotation of the pure enantiomer multiplied by 100. So for example, we have a sample of 2-bromobutane. We don't know if there's more S than R or R than S, but we do a measurement and we see that it has a observed rotation of plus 9.2. So plus 9.2 divided by the specific rotation of the pure enantiomer, which is plus 23.1, multiplied by 100 over 1, and we get 40% EE. So our enantiomeric excess is 40%. The observed specific rotation is positive, so we know we have an excess of the S enantiomer. So the S is an excess because it's plus, and the EE is 40%. So the enantiomeric excess tells us how much excess of an enantiomer is in the sample. So another way of looking at this in terms of enantiomeric excess is if you look at the percentages of the enantiomers that are present. So in other words, to get the enantiomeric excess, you can get the percentage of enantiomer 1, subtract the percent of enantiomer 2, and you get your EE. Let's look at an example. So let's say we have a sample and we know we have 98% S and 2% R. Therefore, the EE is 98 minus 2, which is 96% EE. Let's say we have 70% S and 30% R. Then our EE is 40%, because 70 minus 30 equals 40. An EE of 40% means that 40% of the mixture is the S enantiomer, and the 60% that is left is the racemic mixture. So we have 40% S and 60% as the racemic mixture. To calculate the EE from known concentrations, work out the percent of each enantiomer and then do the subtraction seen above. Now, if you want to know the total S present, then what you've got to do is half the racemic mixture plus the amount of excess of S enantiomer, and that will equal the total S enantiomer present. So let's look at an example. Let's look at the case where we have a 40% EE with being the enantiomer in excess. So we have a 40% EE. So 40% of the mixture is S and 60% is the racemic mixture. So of that 60%, half of it is S, half of it is OR. So 60% multiplied by a half is 30%. So we have 30% S present in the racemic mixture. We knew our EE is 40%. So we have a 40% of S as well. So 30 plus 40 equals 70. So the total S present is 70%. So today's experiment, in this experiment today you will work with two solutions of the carbohydrate arabinose. One solution A that you will accurately make up yourselves contains the L-arabinose only. A second solution B that will be provided for you will contain a mixture of L and D-arabinose in an unknown ratio. You will measure the optical rotation of solution A. You will make note of the optical rotation of solution B. That will be done by the demonstrator. And we'll use these measurements to determine the specific rotation of L-arabinose and also to determine the enantiomeric excess of the solution containing the mixture of L and D-arabinose. So you'll need to write up a lab report for this experiment, consult with your demonstrator in relation to this, and be sure to include all calculations in your write-up.